My name's Kary Rogers, Director, Staff Engineering at Riverbed Support. So my team does backline support, the hard problems, product issues. We interface with development engineering. I came up through TAC, answering phones, helping customers with their problems, went into staff engineering, and then to the dark side to management. So like all of my technical knowledge has been like sort of slowly draining out into just nothing over the last few years. But I didn't want packet analysis to just poof, so I'm trying to drain it out into the internet on a little website that I started called packetbomb.com, with case studies, etc. So I learned packet analysis helping customers solve hard problems with their steelheads, WAN optimization, that sometimes the only way to figure it out is looking at the packets. So I was shown the true power of packet analysis. So we're going to go through some case studies that people have reached out to me with to help them with their problem, or maybe I found them. I don't know. And that's what it says. Yeah. So what I've sort of call it is the packet A team, packet analysis team. I do have a lot of American-centric humor in here. I'm sorry for that. I'm not sure if you know like what the A team is. You guys know what the A team is from the 80s? Some of you look 12. You probably don't. I don't. Even if probably not. But here's my little thing that I don't even know if this is going to work.
Thousands of people turn to the internet for help because they have a burning computer and network problem that they cannot solve. If you have a problem, if no one else can help, and if you can find them, maybe you can hire the Packet A team.
Yeah, right, got it? You get it. You get the idea. All right, let's get into it, guys. First one is slow throughput, and specifically for the first 6.5 seconds. This was a post on Reddit. Sometimes I go look at Reddit, people post their problems, and if you ever read on here, 95% of the answers from people are, oh, check the MTU. And what's annoying is that it's like right half the time. So they keep saying it. I'm like, no, look at the data. So this guy said, we've got these brand new Dell PowerEdge servers. We've got a gigabit switch, and the throughput is not what we expect. Definitely there's like this initial pause, 6.5 seconds, where it hangs before it kind of then goes on. But the throughput is overall is low. This is one where he said we've been looking at this for a month. They probably were swapping cables and doing random stuff as people do. I said, well, why don't you show a PCAP? And I would say probably in the first few minutes, easy to spot the problem. Easy because I've looked at similar issues before. But if he just knew how to like look at the packets a little bit, he wouldn't have been wasting a month looking at this. So let's see if we can do this. I'm going to find where we put the PCAPs. So this is going to be case study 1. Here, you guys can see this. All right, give me a moment to do some. Is that what I wanted to do? I don't think that's what I wanted to do. How do you get out of this? Hit this again. That's what I wanted. All right, let's make it a little bigger. Is that good? All right, so I'm going to do some real quick setup. I'm going to go into the preferences. My layout, I'm going to go over here. That's probably good enough. And the rest of the time we'll just modify our columns. I don't really care about protocol. I want to have, if you do nothing else to your columns, make sure you put in a delta column. Time delta from previous displayed frame. You can right click on, I knew how to right click on this computer. Normally it's, oh, there it goes. I don't know how I did that. Apply as column, you can do that for pretty much anything in here. Yeah, edit column. Edit column. Let's just call it delta, right? And then I'm going to move it over here. And then I'm going to do that. That looks like a... Okay. Seems okay. Okay, so this guy, what? Oh, okay. Sure. Actually, you know what I can do? I have notes over here. I could look at those if I need to. Said, hey, why don't you post up a PCAP and we'll have a look at it. And when I get PCAPs from strangers on the internet, what you get from them is going to vary in terms of quality of the data, what's even in there. You know, the description of the problem, you don't know. So what I like to do when I get a PCAP is just like, what am I dealing with here? So I go up to statistics. If any time there's a problem, just let me know. And I look at the conversations. And I look at TCP. And there's a lot of crap here. So what am I looking for? You know, if it's someone that you're working with, then you can go back and ask them questions. You can kind of figure out, narrow it down on the thing. But if this is like someone on the internet or wherever, or maybe it's someone you're working with across the other side of the world, you know, it takes the back and forth to like get the information. So I just like, let me have a look and see. And he said this is a throughput issue, so I probably care about something with a lot of data. So I'm just going to sort it on bytes. And at the top, there's one that's far and away the most. 420 megabytes, and I see port 5001, and I go, oh, okay. Anyone know what 5001 is? Anybody? Have you heard of a tool called iPerf? Oh yeah, that one. So people, you know, when they're testing throughput, they might use iPerf. So I'm going to filter on that port and just have a look. Oh, it's backwards. Okay, see some stuff. We might want to look at just file properties just to kind of get an idea. 11 seconds. 305 megabits. That's for the whole thing, though. Displayed 340. Okay, just good information to know. So next thing I do is, do I have the three-way handshake? And I do see the SYN, SYNAC, and ACK. So I'm going to go have a quick look. Again, everyone has their own process. I learned a lot from coming here and watching and listening to people like Hansong and Jasper. And then I go back and I do my work, and I kind of take this and take that, and I build your own process. So take a little bit from everybody and build your own process. So I'm looking at, struggling here with the scrolling, options. It's really important to get the three-way handshake because there's so much information in the three-way handshake. You've got MSS, SAC, the window scale, these things you really want to know when you're doing your analysis. So I just kind of have a quick look there, look at the response, same kind of information. The next thing I want to know, have a look at, is the round trip time. And we already kind of know this is servers in the same rack. So we're seeing sub-millisecond round trip time. And we can determine that if we look at the three-way handshake and the delta somewhere in there. And we know here that for the delta is occurring for the SYNAC. So if you think about the the client sends the SYN packet out to the server, that's time 0. That's the start, right? The SYN has to go to the server has to receive it and reply with a SYN ACK back. So that's one round trip. So the delay there, the round trip time, is between the SYN and the SYN ACK. Oh, almost dropped it. If we'd been capturing on the server side, the delay would be between the SYN ACK and the ACK. Again, think about perspective, where the capture is, what it looks like from the client, what it looks like from the server. Because you're sitting there as a server, and at time 0, a SYN shows up, and you immediately send a SYN ACK back. The SYN ACK has to do the round trip, go over to the client sends the ACK back, so the round trip is between the SYN ACK and the ACK. So, a little tip, so you can kind of get an idea of where you're capturing in the network. So now I know we've got the three-way handshake. We've got our options. We've got our round trip time. And I mean, right off the bat, you see some things that are jumping out at you, right? TCP retransmissions. OK. Maybe that's important. I think yes? The delta is the previously displayed packet. So the delta is between the packets that you see right now. You talking about here?
Yeah, correct. I'm looking at packet 719 and 1466. So delta time for 1466 is to packet 719?
19, yes. And this one?
No. Packet number 719 and 1466. 719.
Oh, 719.
Yeah.
Oh, yes.
So the time between 719 and 1466. Okay.
Yes, that is the delta.
Between 146 and 1465. Okay.
Yes. So the delta column, this time 166 microseconds, is after this one, and so on and so forth. So this one is 200 milliseconds after the previous packet.
It's delta time as displayed. There are multiple delta time columns. Choose the one delta time as displayed.
Okay, got it. Thank you.
I personally like to use, let's see, TCP length as a column, so I'm going to apply that. Edit column. And I'm going to hide this one. Just my preference. You do you. Because I'm looking at a lot of the troubleshooting that I do is around TCP, so I'm interested in TCP, and I know the MSS, and so let's have a look and see what's happening. We have our three-way handshake, SYN, SYN-ACK, ACK, and then the client sends a 24 bytes of data, which if you've looked at iPerf, you know that's probably iPerf 2. And then we see data start coming, sending, pushing. So we have this data, and then we have an acknowledgement. So is the other side, the .2, is it acknowledging this data? Well, we can determine that. I also like to have, when I'm doing TCP analysis, it's tough on a screen this size, and I don't necessarily say always have it up, especially if you're getting started, because you don't want to overwhelm yourself with too much information. But I like to have the sequence number as a column, the next sequence number as a column, and the acknowledgement number as a column. Another guy I saw on Reddit, there was another post about TCP dump, and someone was mentioning sequence numbers. And this guy comes on there and says, I've been looking at TCP dump for 15 years, and I've never needed to read sequence numbers. I'm like, what have you been doing for 15 years? There are a number of problems that you will not solve unless you understand what's happening with the sequence numbers. Because TCP is a stream of data. Sequence numbers is how we know where in the stream we are, if we need to retransmit, if something's out of order, or whatever it is. So sequence number and ACK numbers, they're important. So, back to the question. This ACK, which is here, you can see the ACK number is 25. So is it acknowledging this one that has a sequence number of 25? That kind of makes sense. Maybe it is. Or is it acknowledging this one that has a next sequence number of 25? Well, I will tell you. So the next sequence number, so we're sending the beginning sequence number of 1. This is relative sequence numbers. This is setting in Wireshark. You can turn it on or off. Sequence number of 1, we send 24 bytes of data. So the next sequence number we expect to see from this guy is 25. The acknowledgement number means I have received the data all the way up to and including 24, and I expect to see next from you 25. So from that we know that this ACK is only ACKing this 24-byte TCP data segment. And well, you can easily look and see what something's ACKing by looking in the sequence number analysis. And it says, this is an ACK for segment in frame 22. So there you go. So we've sent this packet. What about this one maybe jumps out at you about this one? Jumbo. Now, we are capturing on the sending side. Maybe it's TCP offloading, meaning there's a setting on the network card that can say, TCP, just give me all the data, and I'll break it up into MSS-sized chunks for you, so I'll do it myself to save the CPU of the system and do the work for you, and then send it out in chunks on the wire. Maybe you've seen that if you looked at a capture. Maybe that's what's going on. But how do we know that's not what's happening? How do we know this is really, probably, most likely, a jumbo frame? So we looked at the three-way handshake in the beginning. The maximum segment size advertised by a host that says, in your TCP payload, this is the maximum TCP size I can receive from you. 8960, right? 40 more bytes is 9,000. And from the other side, same thing, 8960. So probably this is a real deal jumbo frame. So we have the ACK, which again is ACKing the one above it. And then we have, if I can scroll, we have a retransmission of sequence number 25, which is back up here, which is this one. And as was pointed out, you can see that came 200 milliseconds. And then we see it again at 400 milliseconds. And again at 800 milliseconds. And one point, did anyone notice a pattern? It's doubling. Exponential backoff. Retransmit timeout. These kind of big round numbers should jump out at you, even if it wasn't like, highlighted in red and black. It should jump out at you. Something is going on here. This is not random. So we see over and over the same segment being retransmitted until we get to this frame here. So we go 200 milliseconds, 400, 800, 1.6, 3.2. What's different about this one? It's not a jumbo frame. 512. That's the amount of data we tried to send. And the next thing that happens is an ACK. And then the ACK number is 537. And you already know how to figure out which one is ACKing, is to find the matching next sequence number. And we just have to go up one. And there it is. So that got through. That was acknowledged. As we scroll down, I will try to do it, we see this behavior now of these 512-byte packets, or TCP data segments being sent and acknowledged. Data, we got data and acknowledgement. So this continues all the way down to here. And then it continues on, and we're sending data, not jumbo frames, but we are sending more than 512, but it's getting through because we're getting acknowledgments. And you can verify this is acknowledging that, this is acknowledging that, and so on. So if we go back up, and we click on that first one, we set a time reference. So now from this packet on, this packet is now time 0 instead of the first one. And we scroll down to at the end of all of this junk, this whatever's going on, the amount of time that has elapsed since we started, essentially, 6.43 seconds. Does that sound like that's pretty close to 6.5? It does to me. So I looked at this, and when you see the same sequence number repeated over and over and over, and it's a maximum segment size payload, immediately I think MTU. And I go, okay, well, you need to check your path, check your interfaces, check your config, figure out what's going on. So first question is, well, what is this? What is this when it switched to 512? Has anyone ever seen that? How did it know to do that? So this specific case was Linux, and there's an MTU probing kernel feature, which I believe is enabled by default, and 512 is a default. So if I'm sending a maximum segment size up to a certain, I guess, timeout value, you know what, let me go fall back to a default value and just probe and see what happens. So that's what it's doing. I think I've asked this before, and someone, I believe, told me that Windows will do the same thing. I don't know which versions might do it. So why, if you send a packet that's too big, why wasn't it fragmented? Could be. Let's look. That's what, in the IP header? Don't fragment. Okay. Maybe that explains that. Well, what should happen if a device is going to drop something because of MTU and the don't fragment is set? What should happen then? You should see some ICMP back, right? It says, hey, sorry, I gotta drop this one, but here's what you should do. Why don't we see that? What's that? You know, in this day and age, that's true. ICMP gets dropped all over the place. People set IP unreachables or no IP unreachables so that it doesn't come back. That's possible. It's not the case here. Have a look at what do you notice about the IP addresses? Same subnet. So what happens on the same subnet? It's a giant frame. I mean, it's an error, right? It gets dropped. So, told them, hey, you need to go check along the path. You've got probably a configuration thing you need to fix. One of the downsides is with helping strangers on the internet is that sometimes they ghost on you, and you never know what the final thing was. But I feel pretty confident about this one. So, any questions before we go back? This was the setup. So, some takeaways for this one. I should say, you need to have your own takeaways. I'm not here to tell you what to do or what to learn. I'm going to tell you some things I think that you can add to your list. Always capture the three-way handshake when you're gathering data, when you're testing something. If If you're working with someone or maybe yourself to reproduce the problem, close the browser, disconnect the mapped drive, close the application, whatever it is, start the capture, then start the connection, map the drive, open the browser. You want to get the three-way handshake. There's a lot of information that could become critical for your analysis. Sequence numbers. Things can get much harder to spot, take longer if you're not seeing the sequence numbers. Again, start slow. Don't, I look at some people's, especially people who have like these huge monitors, the high res. Wireshark fills the screen, and there's a guy at work. He's got, his font is this big, and he's got 50 columns. I'm like, what do you? It's like the Matrix. I mean, I don't know how you do anything with that, but hey, whatever works for you. Start easy. Start small. Again, you see big round numbers, that should jump out to you that something's going on. The little set a time reference, that's handy when you're trying to figure out the timings, but you're looking somewhere down a capture. You're like, okay, this happens, and then this happens, and what's the time difference here? How long does that take? Just set a time reference on the packet at the start. And then you need to know some basics. Path MTU discovery. The MTU probing thing that I mentioned, so you know what that's about. And that's the kernel setting. Okay, I think next is Hansong's favorite video. That's my daughter. She's much older now. And she's still always annoyed by me. Next, slow FTP upload. This was a...
That really was him and his daughter.
Yeah.
For real. Yeah, that's why I laugh every time. He's like, hell out of his daughter.
Yeah, she still has PTSD. Anytime I pull out a horn or a bike goes by, she ducks, Slow FTP upload. This was from an email reader person from Switzerland. Okay, here's a problem. What's the first thing you ask? What changed? Oh, nothing changed. Spend a week turning everything over, doing everything you can, looking over there, and they're like, oh, actually, we replaced the firewall. Like, oh, well, that's nothing. That's, nothing changed. Like, come on. So they replaced their FortiGate firewall with a brand shiny new checkpoint. Their video team uploads files to London, and it was slower than it was before. These guys have a nice, shiny, fast network. They've been fortunate not to really have to deal with these types of performance issues in the past, so they were kind of struggling to understand what was going on. It was 20 megabits. Now they're only getting 5. Not ideal. So they sent me some PCAPs that we will look at. Open this FTP upload and checkpoint. Go. Okay. So, step 1, for me, what am I looking at? Thank you, Mr. So-and-so, for sending me this data that I can help you with for free. One TCP connection. Yay! I don't have to go dig through a bunch of stuff. You've captured the one connection that we care about. And capture file properties. Yeah, right about 5 megabits. So let's make this work. That's fine. We have a three-way handshake. SYN, SYNAC, AC. Options, we have options. 1460, no jumbo frames here. Window scale, SAC, okay. Same thing here, all good. Let's go over here. Next is round trip time, 23 milliseconds. Okay. Kind of got a quick lay of the land. Now, the first thing I do, or the main thing I do, when I'm looking at performance issues, is a handy little tool under Statistics, Stream Graphs, TCP Trace. As you will recall, TCP being a stream of data, sequence numbers represents the data, so bytes. This is a graph of bytes, sequence number, over time, which is what throughput is, right? Megabits per second, bytes per hour, whatever you want to do, whatever units you like. That's what this is. The dark line is the data. So as we move to the right, we're moving forward in time. As it goes up, we're sending more data. The green line above it is the receive window. So you always want some space between your data and the green line so that you have some room in your receive window of the receiver. If we zoom in, we will see data. These little things are individual packets. You can see the little, they're like a little I-beam. That's how big the packet is. The green line underneath is acknowledgement. So here, we send a stream of packets. The green line here is the acknowledgments. When it moves up, it means this data has now been acknowledged. Then we send some more data. And then when this line goes up, that means it reaches the top here. That means these packets have been acknowledged, and we send more data. So over and over and over, we're sending data. So, you know, for this graph, you want to see the line go up and to the right. That's a good thing. Now this one in particular, if we zoom down at the bottom, we can see, it starts off sending a few packets and more packets each time. TCP slow start. You're sending a few packets, you wait, send a few more packets, you keep growing, sending longer and longer packet trains as you go. But what you notice about this is that it's sending a chunk of data and then it waits for it to be all of it to be acknowledged, and it sends another chunk of data and it waits for it to all be acknowledged, which is, you know, kind of typical TCP behavior. But then it kind of just stops growing, right? Each packet train is the same size. So, that looks concerning. I would like to add a coloring rule because this is one that I find helpful when I'm looking at performance. I don't add coloring rules very often. I want TCP flags dot push equals 1. Okay. Oh, and then what's the color though? Let's do background. We'll make it a nice blue color. There we go. Okay. Now, Wireshark 2 has this handy magic scroll bar that gives you like a little kind of lay of the land of patterns you might see. And already, you see some pretty regular patterns. So I'm going to scroll down. I'm going to add another thing that I like to have with throughput is bytes in flight. So bytes in flight is how much data have I sent that's out on the wire that is not yet acknowledged. Applies column. Great. Why can't I go over? Well, that's fine. So I'm going to scroll down, see if you notice any pattern that's emerging here. Right? Over and over and over. Remember this really kind of ugly blue color is our push bit. And most people know the push bit as, I'm a receiver, I'm getting data, and oh, I got a push bit. Let's flush it to the receiving application. It's true. But the push bit is also a good indicator of what's going on at the sender side as well, what the application is probably doing. And what we see here happening over and over again is a push bit at every 8K and 16K, right? When we get to 16K, we stop sending data. Here come our acknowledgments, acknowledge, 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 and then we send data again. And then the bytes in flight start over at 1460, meaning we've acknowledged all the outstanding data, right? This last ACK was 0673. The last data we saw was 0673. We've acknowledged all the outstanding data. And we send 16 more K, and then we wait. 16K, and then we wait. And what was our round trip time? It was, I cannot handle this. It was something, like 23 milliseconds. So we're getting 16K per 23 milliseconds. That's not ideal. So looking at this, and you can see from the stream graph that we're sending a chunk of data. The receive window is wide open, right? You saw the green line was well above the data we're sending. So we're not filling the pipe. And this is the bottleneck on the sending side. So I went to the guy and I said, hey, here's what's happening. Your application, whatever it is that's pushing the data, is doing it in like 16K chunks, and then it's writing maybe it's writing 8K chunks to a 16K buffer, something like that, but 16K is it. That's all it'll do. And then it's waiting. So you need to have them increase the send buffer. It's like, well, that's probably not going to happen. Like, yeah, but so if that's the root cause, which is pretty clear, why did it work before? Like, why would changing the firewall fix it? So they had, this is in production, but they had taken the FortiGate, put it in the lab, and done some testing to see, and sent me the PCAPs from the FortiGate. So let's have a look at that one. Open. And when I open, well, I'll show it to you, but I'm not going to fix it because it'll take too much effort. So this is the LAN capture from the firewall. And you see there's some concerning red and black stuff here, and it looks to be a lot of them. Dupacks all over the place. And if you've taken captures from a firewall, sometimes you see this behavior, and you're like, well, is this a problem or is it not? So if you click on, say, this dupack, my question is, because I've seen this before, are these just duplicate packets in the capture process, or are they actually duplicates on the are these dupacks? So I look at the IP ID, 9606. This one's 9606, 9607, 9607, 9607. So these are the same packet repeated, and sometimes that happens depending on the vendor, how it implements its packet capture. So easy way to fix this, I'm not going to do it, is edit cap. Edit cap comes with Wireshark. Just go to your command line, edit cap minus lowercase d, the name of the file, and the name of the new file you want to write it to. And for me, that pretty much always works for something pretty simple like this. So I've already done that for you. And here we are. So we have this capture. Let's have a look at the stream graph to see what it looks like. Well, that's very different. And I will say that this was in a lab environment, wasn't the same environment, may not even been the same video application. But we can clearly see from this that these packet trains are much longer. They're growing, right? Each time they get longer and longer and longer, which is what you would expect to see. But I skipped a step in my analysis. Sometimes you get lazy. Sometimes you forget whatever it is. I didn't verify. We know we have the SYN and SYNAC here. Right? Here they are. But what do you see that's very different about this one versus the last one? In terms of doing your checklist of like, okay, I've looked at this, I know this. Round trip time. Before it was what, 23 milliseconds? Now it's 55 microseconds? That's interesting. I mean, how could that be? If before, if we're talking, it's 23 milliseconds. Let's have a look at the WAN side. Here, it's about 17. Again, this is a slightly different setup. Let's have a look at the graph. Okay, so we can clearly see the round trip time sending data, and you can see that it's growing each time. We start with slow start, just a few packets. Every round trip, we're sending more and more and more until we send the whole file. So, what does this look like to you? Why does the FortiGate give better performance than the checkpoint? On the LAN side, we have LAN side speed, round trip time. On the WAN side, we have WAN round trip time. It's proxying. Like, did they know they had that feature? I guess not. So what's happening is, love covers a multitude of sins, and low latency covers shitty applications. So if you have an application that will only give you 16K per round trip, and your round trip time is 55 milliseconds, you're probably not going to see the problem as you would when you have a round trip time of 20 milliseconds. And now it's going to be painfully obvious. And you're going to go from 20 megabits per second to 5 megabits per second. So I believe here I think they put the FortiGate back. I think that's what they did. Yeah. Was there anything else I wanted to say about this? Yeah, so another thing that I think is interesting about this one is if they're transferring, this probably isn't a very big file, maybe, I don't know. We could look and see like how much data was sent via TCP. But it's just really starting to ramp up and then it's done. So for things like HTTP, maybe where it's lots of short-lived connections, or if you're sending a bunch of smaller files, what's something you could do that would actually probably increase the performance quite a bit? Think about slow start and how TCP works. So zooming in. So when we start out, we're just sending like one packet, and then 2, then 4, then 8, 16. The amount of data you're sending at the beginning of the connection, that's the initial congestion window. I will send this many packets and then wait. Now I'll double it. I believe Google is pushing for like initial congestion window of 10. I think maybe some browsers, maybe Chrome's even doing that. I'm not sure. So if you did, say increase the initial congestion window to a not much higher value, but a higher value. So you're not starting at 1, but maybe you're starting at 10, then you would probably increase the performance quite a bit too. Okay. I think that's all I wanted to say about that.
So Kary, the 16 milliseconds is for, the other one was 23, right?
Yeah, but there were two different
Two
setups.
different environments.
Yeah. All right, how are we doing? What time do we start? No, don't answer that. Supposed to be done by 5:45. I think we're okay.
Kary,
Yes.
two questions.
Hmm?
The sequence transfer graph, what's the difference between the event graph versus the trace graph?
It's old man versus you.
I made a slight joke, not aimed at anybody, that if you use the Stevens graph, it's probably because you're old and you don't know how to learn new things. Because that's all there was way back in the day. It's not true. It's just a joke.
But it is true.
Well, but you made a very good point, is that as I've been talking about, don't overwhelm yourself with data, and we're going to see in the next one that there's a lot of information presented to you in the stream graph, that the Stevens gives you your throughput with a simpler view. So you're not being overwhelmed by like receive windows and ACKs and SAC blocks and all these things that are there that then when you're first starting out, start with Stevens. Maybe it'll show you what you need. Okay. So the takeaways, again, I hope you have your own. Always look at the round trip time. I've burned myself. A case study I did a couple years ago was also a hidden proxy, but no one knew it was there. And I found it by doing like in-depth protocol analysis of HTTP, finding headers that pointed to a hidden proxy and Googling the string of the product, and that was all fun. But like if I just looked at the round trip time right off the bat and noticed it, I would have known it was a proxy right away. Again, latency is huge for some applications and protocols. So if you're making changes to your environment, moving applications around from data centers or to the cloud or whatever, you've got to understand how it's going to affect the application. We talked about the push bit. I like to, especially when I'm looking at throughput, I like to highlight the push bits so they're easy to see and that can let me know what the application is doing. So bytes in flight. We never got above 16K. Between two endpoints, you've got some optimal throughput or some optimal bytes in flight based on the bandwidth delay product. So if your bytes in flight never reach whatever that is, many times you might go over because of buffers along the path. But if you're not even reaching the BDP, then you've got a problem. Oh, I'm sorry. Bandwidth delay product. So that's the bandwidth times the latency. So think of like a pipe. It's the length and the width of the pipe, how much it takes to fill it. All right, one more. Okay. Anybody know Bob Ross? The painter guy who does like happy little trees? I'm sorry. Just bear with me. Oh. How do I get to it?
Welcome back. I'm Kary Rogers. Thanks for joining me today. First, I want to address something. Some people say, Kary, I can't do what you do. I don't have the talent. Well, that's baloney, because talent is just interest pursued. Now this week, we're going to look at a slow mailbox move. And to do that, we're going to use the almighty Wireshark to look at the happy little packets. Here they are. All those little packets. You can scroll and scroll and oh, there's an ACK. Let's get into it.
All right. Too much time on my hands.
Capture the essence of
All right, this one. Another email reader said they were having data center to data center transfer performance issues in one direction. TCP, specifically. Easily reproducible, FTP, iPerf, didn't matter. One direction's fine, the other direction, it was not so good. So, send me the PCAPs, and we'll stumble through it. Do I have this already? No, of course I don't. So we're going to start on the server side because in this case, the client's pushing data to the server. Let's have a look at our conversations. Hallelujah, we have one TCP connection. We have am I at the top? Oh, there we go. Send, ACK, good. There's some extra little fun bits in there. Does that matter? Don't know. We have, yeah, so you remember earlier, I said when you have to think about where you're capturing. On the client side, on the server side, what's it going to look like as you go down the packets? How is it going to be different? And I talked about how you can kind of tell from the round trip time if it's between the SYN-ACK, the SYN and the SYN-ACK, or the SYN-ACK and the ACK. And here, it is between the SYN-ACK and the ACK, and it's about 41 milliseconds. Is the round trip time. Great. So we do see a lot of red over here, right? We don't know if that's a problem, if that's real or not. You know, maybe we have to do some sequence number analysis to figure it out. We'll see. But let's just have a quick look at what the picture looks like, because I like pictures. Now, there's some big gaps there, and I'll just tell you that that's the capture device having dropped packets. Not big of an issue. We don't see that problem on the client side, the sending side, so let's just look there real quick, just to get a better view of the picture. So, up and to the right, yeah? Now when I look at a picture like this, my first thought is, all right, I know what's happening. We're increasing throughput, because it's kind of wobbly, right? We're increasing throughput, and then it kind of changes the direction, then it kind of goes up, and then it kind of goes down. To me, that says packet loss, because we're trying to increase our throughput. The line is getting steeper, and then it gets a little flatter. And then it gets a little steeper, and then a little flatter. So to me, we're pushing and backing off. We're pushing and backing off. Okay, so I'm prepared to go back to them and say, you got packet loss. You're going to need to figure out where that is. That can be a tedious process. If it's with your provider, then good luck, Godspeed. But I wanted to take, as I kind of looked at it a little closer. Let me go back to the. Oh no, my pre-made filters over there. We'll be okay. Server. So, just kind of scroll through here a little bit. Out of order, dupacks, previous segment not seen. Again, sounds like packet loss. And I'm trying to think, because I had ended up seeing a problem similar to this recently of why when you see these things that tell you XYZ is happening, that's Wireshark giving you its best guess based on what it sees. Sometimes it's right, sometimes it's not. That's why you need to be able to understand where we are in the order of things, being able to follow the sequence numbers. So let's look at an example, and I'm just going to type it in because I already did it over here, and it's a good example. Just bear with me. TCP sequence is greater than or equal to 3940933. Whoop. And TCP sequence. This is somewhat tedious. 9693, and I'm probably going to get it wrong. Or TCP dot next sequence equals 3942393. Almost there. All right, I hope I got this right. All right, what I've done is I've zoomed in on just one little section, and we're just going to kind of look and see if we can understand what is happening here. Okay, so we send a segment. We send 1,460 bytes. we're at sequence number 0933 with the next sequence number at 2393. Next is 5313. Is that what we wanted? No. And it says previous segment not captured. Okay, so maybe we dropped a couple of packets here. Let's see. So the next sequence number 6773, and we get 3. No, that's not right either. So that's out of order. 5313 is the next sequence number expected, and then it's 82. Nope, that's not right either. And we get down here 2393. Oh, that sounds familiar, right? That was the one that was supposed to be up here. And then we get 9693, which actually matches this one. Should have come after that one. And then we have 6773, which goes way back up to here. So this is just, we have a chunk of data. It's just been all scrambled up. Is out of order a problem for TCP? The favorite answer everyone likes to give is, well, it depends. So that's these are the packets coming in. And so what does the receiver do? So we see an acknowledgement of 2393 saying, hey, this is what I expect to see next. And it's ACKing. Remember, it needs to match a next sequence number. That means it's ACKing that first one. Okay, all good. Everything's fine. Then this one comes in, which is 5313, not the one we wanted. So we send a duplicate ACK saying, no, I need 2393 from you. And what it will do, if it's enabled in 3-way handshake, which should have already checked, is a SAC. Selective acknowledgement saying, so I got the 5313 through 6773, which matches this one. I got that. I'm going to save it. But what I wanted was 2393. So what shows up next? This packet. Is that the one we wanted? No. So we send another duplicate ACK saying, I still need 2393. And we're going to expand the SAC block to include these two, because they're just reversed, right? These first two were just switched. That's it. And we get another out of order, 8233, and we send a third duplicate ACK saying, like, I'm trying to tell you, I really want 2393, and so we add another SAC block saying, but I did get that packet. And then shows up the one we wanted, 2393, and then the next couple of packets. So we got it. It was just out of order. So in the meantime, TCP, if I get an out-of-order packet, out-of-order sequence, I need to send an ACK, a dupe ACK, or, an ACK saying no right away. For every one that comes to me out of order, I'm going to tell you which one I actually need and want. So that's what it's doing. For each one that was out of order, I'm going to ACK immediately with an ACK. Normally, TCP is going to ACK, every other packet. So what happens if I'm a sender and I send some data out and ACKs are coming in, and then I get 3 duplicate ACKs in a row to me? What might I do in that instance? Resend it, right? For every segment of data I send out there, I'm setting it aside, I'm starting a timer. And if I don't ever get it acknowledged, when that timer goes off, well, I'm going to resend. I'm going to go back to slow start. We had, a packet was lost. If I get 3 duplicate ACKs, if I get maybe a couple, like, well, maybe things are out of order. So I'm not going to do anything. But if I get a third duplicate ACK, all right, it's probably really lost, and I need to go ahead and resend this. I'm not going to wait for the timer to go off. I'm going to do a fast retransmission, and I can go into fast recovery mode, which is not slow start. So down here, we see 2393, which is, it says it's out of order, but that is the retransmission from the sender. And if we go look at the same set of data on the sending side, which would be the client, what do we see? we see that first data segment, 2393 to 2393. 3853 to 3853. This nice little stair-step zigzag pattern all the way down, perfectly in order. I mean, this is from the sending side, perfectly in order. And then we get an acknowledgement, which again acknowledges the first one in the train here. And then boom, 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 3 duplicate acts. So we're like, oh, we must have had a packet lost. Let me go ahead and resend it immediately. Right? So we send this data, and I think we wait, this is the end of a packet train. We wait the round trip time for these acts to come in. Those are sent, they're out there. It takes 20 milliseconds to get there, 20 more milliseconds for these to come back. And after a round trip time, we get these acts, duplicate act, we resend it. So what's happening is that a little bit of out of order, like I said, it depends. You swap 1 or 2, a little bit here, a little bit there. No big deal. TCP can handle it. It's built that way. But if it's so out of order that it causes enough duplicate acts in this particular TCP stack, 3 duplicate acts will trigger a fast retransmission. Sometimes it might be 2. If it's out of order enough to trigger a fast retransmission, the sender's going to back off. Whoop, we had a packet loss event. Let me back off, start back up. Then these packets are going out of order again. At some point, randomly, whatever it is, they get out of order enough to trigger the event. And that process just repeats and repeats and repeats. So you can do that analysis. I went through it, somewhat quick, but it's hard to follow. It's even like I haven't looked at this capture in about 6 months. And so earlier I was looking at it, I was going like, wait, what is happening again? Like you really have to focus. Go slow. Look at it several times. Get out a piece of paper and draw diagrams, whatever you need to do. But this is a skill you need to be able to do, is to follow along the sequence of events with the sequence numbers. You can also do, you know what? We're going to look at the Stevens graph. Just for you. If you, you can do the analysis with just this graph as well. If you zoom in on a place where the angle changes, let's say right there, I think. Now remember, further to the right is later in time. Further up the y-axis is more data being sent. So if you see, so the little dots is the data, right? So if you see a dot like this that's off to the right and it's below something that's already been sent, it's either really delayed or it's a retransmission. So if we zoom in, so if we go straight back across to that point, so the lines here connect the order that the packets arrived. And you can see packets arrive, and maybe they're so close together, but we'll try. And then more data is coming in, so the lines connect up here, but eventually it goes back down, all the way back. So now this is data in the stream of things that occurred before, right? So the lines go all the way back down to this late packet here, and then go back up. Kind of, again, that's kind of hard to follow. But from the graph, if you follow, like connect the dots, like when you're a kid, you get 1 to 2 to 3 to 4, it makes like a picture of a frog. You follow the line here, and you should not be going back down like that later in time. So you know that that was out of order. And if you look at the TCP trace, there's even more information in there. So you see these red lines are SAC blocks, which we talked about the SAC blocks. And you can see that it's so close, though. You can see that some of them arrive out of order based on, like this one right here that I have the hand on, it's further to the right, but the one above it is to the left of it. Doesn't make any sense. Again, this tool is your friend, but it takes time. So again, just keep using it. And I honestly didn't even realize that part looking at this graph until I looked at this several times. So yes.
Can you go back to the graph and
Same one?
say that once again about what is to the right, what is to
Yeah.
the left?
So remember, whoop, each little line is a packet. As they stack on top of each other, that means data further in the stream. You know, it's a sequence number, right? So it's going higher, and to the right is later in time. So if you have a packet like this one, well, if you're moving to the right, you have this packet that my hand is on. In terms of time, the next one that arrives is up here. So we skipped this one, right? So you should not have a packet that is further to the right and below one above it. That's, yeah. It's hard to wrap the head around. It's probably easier with the Stevens graph, honestly, because you can follow the line, and it should be constantly going up and up and up, not loop back down.
So what's the difference between the green line and the red line?
Yeah, the green line is the ACK. The red line are SAC blocks. So that means you remember in the options we had. So that's what that red line denotes, is that we had a SAC block in that ACK. Okay, so to wrap this one up, because we're running out of time here, based on where the capture was, they were able to narrow it down to the edge router, which was a Juniper, and they just replaced it with Cisco, and the problem went away. Yeah, I mean, well, you know, I was like, well, did you open a case with Juniper? Maybe there's a known bug. Like, no, we didn't do that. Like, we don't have time for that. I mean, I guess they had the equipment. It was an easy thing to do. You know, again, getting details out of people after their problem is resolved is very difficult because they don't really want to come back to it. Okay, so we're about done here. We got one more video. Takeaways, stream graph. Again, that was a really complicated example of doing, again, you could have done the entire analysis just from the stream graph or the Stevens graph, but that's advanced, right? You need to be able to read the sequence numbers first. And again, the angle of the line, when it changes, something is happening. If it goes up, if it goes down, whatever it is, we're either increasing or decreasing throughput. Go zoom in at that point and see what's happening. Again, just go slow, double, triple check. I have to do that still. And in this case, it really, if I had just had the end with the out of order, or I'm sorry, the other end with the dupacks, where the client that was sending, because it was all perfectly clear, then your dupacks and the fast retransmission, it looks like a packet was lost. If I didn't have visibility on the other end to see how it all arrived out of order, wouldn't have spotted the issue. So you can't always get captures from both ends, but if you can, God bless you. All right, this is my newest one. I did it just before Europe SharkFest. Enjoy. Another American syndrome.
Is it a network problem? Is it an application problem? Do all your SNMP and NetFlow graphs look fine? Are you tired of playing the network blame game? Maybe you've tried finding some lost packets. You've probably even tried swapping the cables. If you've tried everything and still can't find the problem, you need Wireshark. Wireshark lets you look directly at the packets on the wire. No more blame game. you'll save the day and be the hero. The best part? Wireshark is absolutely free. But that's not all. Included with Wireshark is edit cap, merge cap, reorder cap, and many more. When network problems get you down, turn to Wireshark. Wireshark is provided in many languages at no cost to you. Learning to use Wireshark will cost you time, practice, and training. Attendance at SharkFest is highly encouraged. Wireshark is not responsible if you read the packets wrong and tell the server team they have a server problem when it's really your 10-year-old firewall dropping packets.
All right.